Welcome to radius of convergence. So in the previous video, we talked a little bit about kind of what it meant for a power series to converge at a specific x. We get a pretty cool theorem about where our functions converge and where they diverge. So our theorem is if we have a power series, a power series in X centered at C, then one of the following statements is true. So our first statement is that the series converges at X equals C only. Right, so essentially only when we're basically plugging in 0 to the untranslated series. The series converges everywhere. So for all X is our second option. And our last option is that there exists a capital R greater than 0, such that the series converges for all X with absolute value of X minus C being less than R, and diverges for all X with the absolute value of X minus C is greater than R. So essentially what this is saying is that we have our C. We go some distance R to both sides. We subtract R and add R. Anything within that interval, we have convergence. Anything outside, we have divergence. So this is one of the reasons that we say our power series is centered at C, is because that C is right in the middle of the region where it converges. So for a definition, we call this R the radius of convergence. In the case where there's convergence only at X equals C, we say the radius of convergence is 0. So in the case the series only converges or converges at X equals C only. So in the case the series converges at X equals C only, we say that R is equal to 0. And in the case where the series converges everywhere, we say R is infinity. So again, if you look at that little picture I drew above, you can imagine if we converge only at C, we go no distance to either side, so that radius of convergence was 0. If we converge on the entire number line, then we would go infinite distance to the right and infinite distance to the left, giving us that radius of convergence, infinity. Just a quick note, this radius of convergence, the theorem we were just looking at, says nothing about what happens at exactly distance r. So if you're at exactly distance r, you may converge, may diverge. But if you, as long as you are within distance r, closer to C, right, then we converge. If you're farther away, there's divergence. So here, basically, we will want to use all of our, we will want to be able to use all of our possible tests for convergence to try to find this radius of convergence. So just a note, to use or to find the radius of convergence, we will want to be able to use our convergence tests. But this gets complicated by the fact that that x minus c to the x minus c may be positive or negative. So this is complicated by the fact that x minus c may be negative, right? Or is sometimes negative. Right? And a sub n as well may be negative. So we get a rather nice theorem that allows us to avoid this complication or work around this complication. I'm going to just pause my video and do some quick readjusting. So the theorem that we get is that the radius of convergence of power series, the sum from n equals 0 to infinity of a sub n times x minus c raised to the n is the same as the radius of convergence of the sum from n equals 0 to infinity of the absolute value of a sub n times x minus c raised to the n. So essentially, we can just look at absolute convergence, right? We can just take the positive version of our series and then find the radius of convergence from that, and it will be the same as the original series. So this will allow us to apply all of those various tests that required our a sub n's to be positive. So let's go ahead and do an example. Let's find the radius of convergence of the sum from n equals 0 to infinity of x plus 4 to the n over n factorial. So note here, that we can, by the theorem above, we can simply look at the positive version of this. So we can focus on the sum from n equals 0 to infinity of the absolute value of x plus 4 raised to the n over n factorial. Having that nth power up top, the factorial down below, this lends itself very well to the ratio test. So from here, we can use the ratio test to check for convergence. So our a sub n would be absolute value of x plus 4 raised to the n over n factorial. And our a sub n plus 1 would be the absolute value of x plus 4 raised to the n plus 1 over n plus 1 factorial. So the ratio test says that we should look at the limit as n goes to infinity of a sub n plus 1 over a sub n. So we are looking at the limit as n goes to infinity of the absolute value of x plus 4 raised to the n plus 1 over n plus 1 factorial, all over the absolute value of x plus 4 raised to the n over n factorial. This is the exact same thing, doing a little simplification, as the limit as n goes to infinity of absolute value of x plus 4 over n plus 1. X is fixed. X is not changing. It is only n that is changing. As n goes to infinity, a constant over n plus 1 will go to 0. So this is less than 1. So by the ratio test, I should say that this is for all x. So by the ratio test, we have convergence for all x. So by the ratio test, the series converges for all x. Which means that we have our radius of convergence r would be equal to infinity. Next up, let's find the radius of convergence of. I'm going to slightly change this. Let's make this the sum from n equals 0 to infinity of -2 to the n times x plus 1 raised to the n. So again, by the previous theorem, we can just focus on the absolute value. So by the previous theorem, we can instead look at the sum from n equals 0 to infinity of 2 to the n, taking absolute value, times the absolute value of x plus 1 to the n. So This looks like it lends itself very well to the root test. So this lends itself to the roots test. So we have here our a sub n is 2 to the n times the absolute value of x plus 1 raised to the n. The root test says we should look at the limit as n goes to infinity of a sub n to the 1 over n. So we're looking at the limit as n goes to infinity of 2 to the n times the absolute value of x plus 1 raised to the n, that whole thing raised to the 1 over n. This simplifies nicely just to the limit as n goes to infinity of 2 times the absolute value of x plus 1. So for the root test, we get convergence as long as this is less than 1. If we take this limit, we have no n's involved. So we just have 2 times x, absolute value of x plus 1. Right? So we get convergence whenever this is less than 1. So we need 2 times the absolute value of x plus 1 should be less than 1, or the absolute value of x plus 1 is less than 1/2. This right here immediately gives us our radius of convergence. So our radius of convergence is 1/2. So just a quick note. Let me actually change colors. So note, we know that the series converges on the interval from -1 minus 1/2 to -1 plus 1/2. So in other words, the interval from -1.5 to -0.5. And we know it diverges on the interval from -infinity to -1.5, the open interval, and from -0.5 on to infinity. The question is, what is happening at -1.5 and -0.5? So, but what happens at -1.5 and at -0.5? And the answer to that is you have to just plug it in and try. So answer is you have to plug them in and try. So at x equals -1.5, the original series, we had the sum from n equals 0 to infinity of -2 to the n we're times x plus 1 to the n. So we would have -2 raised to the n times -1.5 plus 1 raised to the n. So this is the sum from n equals 0 to infinity of -2 to the n times -0.5 to the n, which is just the sum from n equals 0 to infinity of 1 raised to the nth power, which definitely diverges. And then at x equals -0.5, we have the sum from n equals 0 to infinity of -2 to the n times -0.5 plus 1 raised to the n, which is the sum from n equals 0 to infinity of -2 to the n times 0.5 raised to the n, which is the sum from n equals 0 to infinity of -1 raised to the n. So this will be 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, this never settles, this diverges. And so we can definitively say that the series only converges on that open interval in this case. So our interval of convergence would be -1.5 to -0.5. So again, that theorem that gave us the radius of convergence tells us nothing about what happens on the endpoints. So if you want to actually figure out the precise interval where your series converges, you need to simply plug in your endpoints and just see what happens. Right? So that is radius of convergence and figuring out sort of where our series makes sense.